Hello, everyone. So we're going to get started in just a minute. We're going to give people a few more moments to join us. And we are going to ask that everyone mutes their mic unless they are asking a question or adding to the discussion. So again, we're just going to give people a few more minutes to join us. And I want to ensure everyone can also see my screen. So if you can see my screen, just give me a +1 in the chat. Great. Great, thanks everyone. Okay, and it looks like we do have a majority of the members currently with us already, so including our author of this research paper. So I think we can go ahead and get started. And I'm going to start off with some general introductions and then giving you some guidelines as well of how these sessions are run. And then we'll go ahead and dive into the research paper itself and then start a discussion with the rest of the group. So first, before we begin, I want to introduce myself. My name is Laura Montoya. For those that have been with our Meetup group for some time, you probably are pretty familiar with me already, since I've been running this group for about 2.5 years. I took it over from a good friend of mine, Abhishek Sharma, who actually started the group originally, but has since gone on to do other amazing things. And of course, I've been supporting this group through my own organization, the Accel AI Institute, which is a 501c3 nonprofit organization. And I do want to introduce as well the researcher on this paper, one of them, of course, who's joining us today, Pablo Samuel Castro. Pablo, do you want to unmute yourself and say hi to the group?
Yeah, hi everyone. Pablo, happy to be here. It's great that you're discussing this paper. We're really proud of the framework. Yeah, happy to answer any questions after the discussion or during the discussion.
Thank you, Pablo. Okay, so a little bit of information in regards to this group itself. Obviously, we're a Meetup group. You can find us at meetup.com under Artificial Intelligence and Deep Learning Enthusiasts. We also have a GitHub through the Accel AI Institute, which is also linked here. And I will be sending out a copy of these slides as well after the discussion for everyone to reference. And also you should know that this call is recorded through video. So we do upload this usually to YouTube. So I just want to make everyone aware of that, that this will be publicly available both for your own reference in the future, but then also for others that couldn't join us today that want to watch this and learn about the framework itself and how we're discussing it as well. And if you want to learn more about the main organization, Accel AI Institute, you can find us at www.accel.ai, and our subsidiary, the Latinx and AI Coalition, which you can find at latinxandai.org. For these discussions, I want to preface this by saying this really is meant to be a full discussion and not like a presentation or a lecture. So although I have prepared slides to go over different parts of the paper itself, I'm going to stop pretty regularly and ask questions of the group. And also, I would like you to stop me at any point, ask questions, add to the discussion or insights from other things that you know or that you've learned by reading this paper. So please try to make this as interactive as possible. I do not want to just lecture to you guys for the next hour or so. But with that in mind, we do ask that people try to read the paper in advance and find a few good questions or insights, that people try to be on time as much as possible because latecomers can be disruptive. Use a headset in a quiet location if possible with a good internet connection. And then do have the discussion paper on your desktop ready to show via screen sharing if you want to point to a specific figure or something else, another reference as well that you would like to point out to the group. Of course, please understand there are no silly questions. We're all learning. Deep reinforcement learning and reinforcement learning itself is an area that is changing constantly. New research is being published every day. And so no one here is expected to be an expert. And we want to make sure that the barrier to asking questions is very low. So do not be embarrassed by that at all. And of course, the AI and deep learning enthusiast has strict guidelines regarding any discrimination for any reason based on gender, ethnicity, sexual orientation, class, or so on. And then anyone that does violate that guideline will be removed from the group immediately, not just the call. So I want to stress that and make it very clear. And then I do have to point out that since we are a 501c3 nonprofit, we of course appreciate any donations that you can make to our organization. And you can do that through the Accel AI Open Collective that is linked here as well as on the Meetup page. So any quick questions before we start off with the research paper itself? And also of note, if you don't feel as comfortable unmuting yourself and speaking, you can also put questions in the chat. I'm happy to read those for the group and then also try to answer them. Or if anyone else wants to add to answering questions in the chat, you are more than welcome to. We want to make sure everyone feels comfortable in engaging in whatever way is best for them.
Can you please share the link to the paper? Sorry, I didn't read it. But
yes, so the paper is linked on our Meetup page. So if you're on meetup.com under AI and Deep Learning Enthusiasts, the PDF is right here. And this is the white paper for dopamine.
Thank you.
Yeah, not a problem. Okay, so we're going to go ahead and get started then, if there aren't any other questions about how these sessions are run. So a general introduction, dopamine is a deep reinforcement learning framework which involves complex agent-environment interactions. Now I've added a lot of pictures to these slides just because for myself, I'm a very visual learner and I figure it would be helpful to others as well. So here you can just see an image of what a complex agent-environment interaction looks like. So that includes an agent with an internal state of the environment that it's in. That will then perform actions in order to get a reward. And so that reward in these cases could be moving through that environment itself, finding the end goal, or of course increasing the number of lives and so on. And so it does that by observing the environment, performing actions, getting a reward or not getting a reward, in this case, sometimes being discounted, and then readjusting its internal state based on that environment and its interactions as well. Dopamine itself is TensorFlow based, and this is composed of 12 Python files and about 2,000 lines of code. You can find the code itself on GitHub. It's listed here, and I also listed it within the Meetup group. And there's also a collab that's available if you would like to run the code without necessarily setting it up locally. You want to just do that through their GPU online. So this is a value-based deep reinforcement learning framework. And so there are a couple different kinds of deep reinforcement learning frameworks that are focused on different areas of reinforcement learning. So this one specifically is based on the value function rather than policy-based. In the conclusion of this paper, they talk about how in the future they would like to implement additional methods that are also policy-based. But for starters, currently the framework just focuses on value functions. So of course, the goal of this is to find the maximum value achievable under any policy. And through value-based deep reinforcement learning, you can do different kinds of research. So some of the examples that are given in the paper here are architecture research, comprehensive studies, visualizations, algorithmic research, and instruction. So dopamine specifically in its current state focuses mostly on algorithmic research and instruction, and not these other areas, the architecture research, comprehensive studies, or visualizations. And they talk a little bit about the DeepQ Network, which was originally published by DeepMind in Nature. OpenAI has an implementation of this, which has kind of created the baseline for deep reinforcement learning. It is very complex, though. It consists of about 6 modules. And the DQN shows an innovative use of the agent architecture. So this includes a target network, replay memory, and Atari-specific pre-processing. And you can see the performance of this DQN network here. This was actually published by the OpenAI implementation. I'm not sure exactly when. I think it was like a year or two ago at this point. So before moving on, I want to see if anyone has comments about the OpenAI implementation or DeepMind originally creating this DeepQ network.
Is the implementation anything related to, does it have anything with the TensorFlow library, or it's an independent implementation?
So OpenAI, in my understanding, its implementation was done in TensorFlow.
Yeah, that's correct. Both the OpenAI and Dopamine were both using TensorFlow.
Any other questions or comments on this part? Okay. So the next section of the paper goes into software that is developed for deep reinforcement learning research. And specifically, when software is developed for this type of research, researchers have identified some critical operations that they would like to have available or implemented within the software. So part of that is component modularity, automatic differentiation, and visualization. So you can see that through these images here, when you're using an environment that's simulated, either an arcade learning environment, a continuous control environment, first-person environments, or real-time strategy games, this is what it'll look like as the system is actually, or the agent's actually playing the game. with dopamine, they chose to specifically focus on arcade learning environments over these others, again, for simplicity and to ensure that this is really used as a tool for teaching and for learning, as it, people are really trying to develop algorithms for this type of work. And they did a case study here on the DeepQ Network architecture. So when looking at architecture research, that really focuses on the interaction between different components, their network topologies, as well as using agents that are composed of multiple interacting components. Rather than in algorithmic research, here it really focuses on improving the underlying algorithms. So those affect the learning and the behavior of the agent itself, which is not tied to the agent architecture. And this image just shows an example of how a DeepQ network would look if you're trying to solve a specific task. So why don't we take a moment and just look at this image itself. Can someone, any volunteer, kind of explain to me what's happening here in this image? And please don't be shy.
I think what is probably is happening is that the pixels, color pixels which are there, the red, blue, and green, they are going through this network, and after that, the network, the deep network, the layers in that have learned or are learning to then decide, depending on the pixels which come in, what action to be taken. So that's what I'm trying to see.
Wonderful, thank you. Would anyone else like to add to that? And sometimes if we don't get a lot of volunteers, I will just randomly unmute people and ask you to step up. So please, let's see if someone else has another interpretation or wants to add to what's happening within this image here. Okay, so we have a question in the chat that says, what is the relationship between the pixel values and the Q value? Anyone want to take a guess?
I think the Q value should be what comes is from the table that will be the output from here on the right. And the pixel is basically the input which passes through this network, and then the network creates a set of values. The resulting values are the Q values.
Great. And is there, so as you're describing it, Cyril, are there more than one Q values?
Correct. There'll be, there should be a 1 Q value, but the resulting value should be a 1 Q value based on the action that is there. So for every action, there's 1 Q value. So there are 3 actions there. There should be 3 Q values. I mean, Q is should have 3 values there, as I see.
Okay, but how is that related to the pixels itself? So I understand what you're saying for the actions of the dog to turn right, turn left, or go straight. But in its processing of the camera image through the red pixels, green pixels, and blue pixels, are those specifically related to the actions taken that are derived from the Q values?
Now you've got me thinking.
And anyone else also, feel free to jump in.
They should be. They should be related, but I'm trying to figure it out.
Sure, and we do have some other comments in the chat as well. So it looks like here people are saying that the function is approximated by the network parameters. That's from John Martin. And Ravi has stated, I believe there are 3 discrete Q values. And Mikal has said the input image represents the current state of the agent, or at least what it sees.
So basically, if it's a value function, then it will choose the value which is the what we would say is the optimal value for it, or the best value, and going forward to it. It has 3 Q values. It will take the highest or the best value and then take an action related to that.
Yeah, so usually in reinforcement learning, the goal is to optimize your position and take the best action related to that optimization, right? So that is correct. And it looks like also John Martin has said the agent chooses the action associated with the highest Q value. And let's see. And Hui Chan has said Q is the action value, the image pixel is the input from the environment. Yes, that is correct as well. Okay, and we do have another question here from Oswald. How is the highest Q value associated with one of the 3 possible movements? Right, straight, and left. So that's a great question.
That will ultimately be decided on the reward. Like when you go ahead and see what reward you get, if you get a reward, then the Q value of that, you go back and update the Q value and the value, and you start increasing it. If I take a certain set of pixels which come in, and that pixel results in an action, and that action results in a reward, then the Q values going back are updated to the higher value, and that action is more favorable then.
I would agree with that. Okay, and it looks like we have some other comments in the chat as well. So Thomas has said, assuming the network is convolutional, the relationships in the pixels get mapped to the Q values. So lines and features in the images get associated with the correct action. Okay, and then Klee has said, this diagram does not say what action to take when there are ties in the Q values. That's correct, that's not very clear from this image. And Ravi has stated, I think it's more of a feedback loop. The agent changes its position continuously based on the feedback loop of pixel values and the Q values. And then Oswald has said, ties are probably resolved by a random selection.
As per my understanding, we are taking here 3 different channels from the camera image, and this convolutional network is responsible to collect the sample episodes. And in further, when we are going to train the network with the feedback mechanism, then these episodes will be used as like training data and the testing data in that scenario. So since this image does not depict what is the right action or what is the most valuable Q value or optimum Q value, but seems like this is a way where we are collecting most of the samples.
Yes, I would agree with that as well, Rahul. Thank you. So there are some other comments and questions in the chat as well, but I think we should move on to ensure we get through more of the material. So this is a really great way, though, to start thinking about, well, what is a DeepQ network if you're not really familiar with how it works and how the architecture works. But we can go into that as well more in depth at the end of the call when we do an open floor for discussions. So further on in this research paper, Pablo and group talk about how the Q learning robustness is increased. And so they do this through double DQN and gap increasing methods, which prioritize experience replay, frequent sampling of the state, and high prediction error. It also includes a method called retrace, which computes the sum of n-step returns. And this is weighted by truncated correction ratios derived from policy probabilities. So every time the system does something, that return is added to the n number of steps, and it's all summed together. And then, of course, it also takes into account those weights, depending on the probability of whether that action was correct or not. At least that's my understanding of it. And it also includes the dueling algorithm, which separates the estimation of Q values and provides an advantage and baseline components for this type of research. And last, it includes distributional methods, which introduce new losses to the algorithm and replaces scalars made by the DQN with the value distribution as well. Are there any other questions or comments on this?
So just to clarify, these are not all included in Dopamine?
Yes.
So these are kind of enhancements that have been made since DQN was introduced by a bunch of different papers. So prioritized experience replay is in Dopamine because that's a part of the Rainbow agent. But things like the importance sampling importance ratio correction with retrace, we don't have that, nor do we have dueling algorithm and things like that.
Wonderful. Thank you, Pablo. Okay, and then the other thing that it talked about, and again, this is also not included in Dopamine, but is something that's been thought of as important for DeepQ Network architecture, and it's often used in this type of research, is visualization. So this focuses on focused interventions, which give you a deeper understanding of deep reinforcement learning methods. Here, performance is not necessarily emphasized, and it's not restricted to visual analysis either. So of note within the paper is that a majority of the research does focus on visualizations, probably because it makes it easier to understand and interpret those results. But in this case, it was not included. And I wanted to include another image, a more simplified image of the DeepQ network architecture, just to give people an opportunity to understand what's actually happening within this network as compared to other types of neural networks and reinforcement learning networks as well. So any other comments or questions on this before we move on? No? Okay. So let's go on to the next section. So this talks about how are research objectives enabled by software. So why would a group decide to develop new software frameworks to help do research in the future? Because that's obviously the goal of Dopamine. And so it was discussed here that you really have to compare existing code availability versus new code that has to be written every time you're doing this sort of research. Also, the shelf life of code that's written during the research itself. That's something, if you have to consistently rewrite code whenever you're doing additional algorithmic research or architecture research, oftentimes that'll impede your innovation and your ability to move forward in the work. And then also the value of that high performance code and the code complexity. So here they describe, whether that's a complex framework or a simple framework, obviously complex being large, modular, and abstract, and a simple framework being compact, monolithic, and readily understood. Although I will say, in my experience, I find monolithic code harder to understand, but that just might be my own training in engineering. But this is how the researchers here describe the difference in code complexity that's developed for research objectives. And then They, of course, state that dopamine positions itself on the side of simplicity, aiming to facilitate algorithmic research and instructional purposes. So that's really the goal that they had in mind when developing this framework itself. And so some of the design principles that they came up with when developing this framework is they wanted to allow for easy experimentation and make it easy for new users to run benchmark experiments, for flexible development, to make it easy for new users to try out different research ideas, to make it compact and reliable, to provide implementations for a few battle-tested algorithms that are already available and being used by other researchers or other research groups, and so that it's reproducible. So this facilitates reproducibility in the results, of course, so others can test this as well. I'm going to stop there for a second again, just to see if there are any other comments or questions on why dopamine was designed the way that it was.
So when it says here, the compact and reliable provide implementation to some battle-tested algorithms, which are those?
So you're asking which algorithms are considered the battle-tested algorithms?
Correct.
That they designed around?
Yes.
Yes. So I know they specifically talk about the established agents that they reference, but maybe Pablo can give a little bit more insight into other algorithms that were used.
So the algorithms we're referring to here are exactly the agents. So it's DQN, because this is kind of what kicked off the deep reinforcement learning revolution. And then on top of DQN, we wanted to include some state-of-the-art agents. So we included Rainbow, which was published last year, but it's a Rainbow Lite. It doesn't include all of the components that they tested in the paper. It only includes the ones that gave the best performance. So these were end-step, distributional, and prioritized replay. And so by adding distributional methods, that means we could also provide C51, which was the algorithm that was introduced in the original distributional RL paper. And this one is essentially the same as Rainbow, but without end step and without prioritized replay. And then finally, we also included an implementation of IQN, implicit quantile networks, which was published at ICML last year by DeepMind as well. And that was kind of an extension of the original distributional algorithm, C51.
Wonderful. Thank you, Pablo. Go ahead, Cyril. Did you have another question or comment?
No, I was just trying to absorb in getting through the network, all these algorithms. That's quite a big list.
Yes, and we'll go into those a little bit more in detail as well further on in the slides, if that helps. And of course, we recommend referencing the papers that were referenced in the original research if you want to learn more about each of those algorithms or how they were published. So we do have another question from the chat here from Clee that says, Pablo, can you please elaborate further what exactly do you mean by reproducible in this paper, especially in the context of networks that would be trained?
So we mean a few things. The first is that the code is out there. So a lot of papers, now less and less, thankfully, but a lot of papers will publish an algorithm and not release the code. So that forces people in the community to have to re-implement the agents. So DQN, for instance, there's like over 200 implementations online, independent implementations of DQN. So this causes a problem because then which of these implementations do you use when you want to benchmark against DQN? So these, all of the agents that we're providing here, I mean, we have Mark Belmar on our team who was an author of all of these papers. So it's kind of like author approved. Then the other, one of the other notions of reproducibility is that we use the gin-config framework. And this one allows you to specify in a single file all of the hyperparameters that you use. So if you do come up with a new algorithm, you can clearly indicate what are the hyperparameters that you used to produce the code. So Gin allows you to do that very easily. And then finally, I did provide, for all of the plots that we include in the paper, I did provide the trained agents, so the checkpoints, along with the statistics file that were produced while the agents were training. So you can plot these in Colab. If you develop your own agent, you don't have to retrain all of the agents. You can just immediately benchmark against the ones we provide. And there's also that website that I made with the plots that they're just encoded as JSON files. So it makes it really easy for you to look at the different dynamics of the algorithms on the 60 different Atari games. So that's what we meant by reproducible.
Thank you, Pablo. And there's another question here from John.
So the quantile regression.
Yeah.
So we did actually implement this at one point. This was before IQN was published. The reason we decided not to release the quantile regression agent is because we didn't want to be a framework where we have every single possible agent ever published, because it would be really hard to maintain that. Right when we wrote Dopamine, it was 4 of us. Right now, it's mostly just myself working on it, and a few other people help when they can. And so we didn't want to add too much on our plate. The other thing is, along the lines of simplicity, we wanted to keep it as simple as possible. So the standard baseline, which is DQN, along with whatever state of the art at the moment. So if another algorithm comes along that beats IQN and beats Rainbow, then what we'd likely do is implement that algorithm and get rid of one of the agents that's no longer state of the art, so that we keep it kind of nimble.
And there's another question from Matt Pinner that I think was actually sent to me privately, but he said, how long have you been working on this? So I think that was meant to Pablo.
Dopamine, so we launched it last August, and we started working on it like in November or December of the previous year. So I guess like 10 months. About 10 months. But again, we weren't working on it completely full time because we're also researchers. So we sometimes would switch off of Dopamine to work on research papers. And then when the deadlines passed, then we'd come back to Dopamine. And yeah, but overall it was about 10 months. And we're still working on it.
Thank you. Okay, so let's continue and go a little bit more in depth about the architecture of this specific framework itself and the design. So here in figure 1 that's referenced in the paper, you can see the life cycle of an experiment. And again, the framework is meant to be very compact and self-contained. So it's only about 12 files and 2,000 lines of code. The main components included are a runner class, and this allows for interactions between the agent and the arcade learning environment. So this takes steps and receives observations based on its position. And here you also do booking, which includes checkpointing and logging of what's actually happening within the space. And the next portion that's pointed out is the check pointer. So this does regular saving of the system and the state itself. And then this also includes a learned weight reuse so that the agent can, run that through the next iteration as well. And then you also have the logger under logger.py, and this saves all of the statistics. So that's accumulated training and evaluation rewards. And this information is stored in the disk for visualizations. After that, you have the agent classes. So here is where you have the core logic for inference and learning. This receives the Atari 2600 frames from the runner. It returns actions to perform the new or the next step. And it also performs learning using the replay memory. Let's see. And as Pablo described earlier, this takes or makes use of 4 established agents that have been used in research previously. So that includes DQN, which is the base class for all of the agents. C51, which is a parameterization of the rainbow agent. The rainbow agent, in this case, which is just simplified to a single GPU, and the IQN agent as well. And the rainbow agent has different components within Dopamine. So that includes the end-step updates, prioritized experience replay, distributional reinforcement learning, and what it does not include in this case is the double DQN, the dueling architecture, and noisy networks, which Pablo described earlier. And if you want to look at code examples for how there are different performance modifications using this framework, you can see that in appendixes B and C. And when you want to set up this system, you want to change that gin config file, which Pablo described earlier. And here this allows you to do changes within the default parameters. It utilizes what's called parameter injection so that it changes these dynamically as well. And all of these parameters are included within a single file, again, to add to that compactness of this framework. So further on in the paper, they describe how you would change these parameters to conduct different specific experiments, which they'll also go into further on as well. So before we move on, are there any other questions regarding the specific architecture of this framework or how it's currently designed? And it might be useful to also look at this within the GitHub repository so you have a better understanding when you're looking at the code, how it looks. Okay, so here's a question from Oswald. Any more details about the TF construct? Is there a Keras construct as well?
So Keras is a part of TensorFlow. It's one of the things, being a company with so many people working on the same things, that you often end up with similar implementations, multiple implementations of similar things. And so we were using slim layers at the time because it's just what we were most familiar with. We do want to switch towards Keras at some point. Right now, in practice, it won't really affect anything. There shouldn't be any difference. Under the hood, I think now they're essentially the same thing. It's just what you call them in your Python code. So at some point, we will switch to Keras.
Okay, and an off-topic question, is Zoom going to be available offline? We are recording this call and we will be posting it on YouTube. So anyone that wants to use this as a reference, or if other people want to learn from this, that will be available, yes. Okay, any other comments or questions regarding the design or architecture of this framework? Or the use of the gin config file for implementing the default settings or changing those? No? Okay. So, oh, here's a question. Why did you use gin? How is this use beneficial?
So gin, if you're not familiar with it, is a Python injection framework. The reason we used it is, there were a number of reasons we wanted to use it. The first is it allows you, as I said before, it allows you to have all of your hyperparameters specified in a single file, because you don't always use the defaults in your for your arguments. And so that makes it really nice. If, for instance, there's the gin file that we use for the dopamine settings, and then there's gin files that are the settings that were used for each of the algorithms in their published versions. But then the other reason we wanted to do this is because it avoids us having to either create some type of dictionary or something that we pass around that contains all of our hyperparameters, because there's a single entry point for the binary, that's the train.py, but you have to send in a bunch of information to the agent, and then other information to the replay memory, other information to the checkpointer, etc. And so if you wanted to do this in a kind of non-ugly way, you would one of the ways you could do this is creating a dictionary and passing that to everybody else. But again, that makes it kind of difficult to keep track of what hyperparameters you're using, because you would have to, I guess, pass it in as flags or something like this. So we found the gin-config quite elegant, and it allows you to pass in any Python structure as a parameter into a function or a class constructor. So that's why we chose gin. Thanks for the question.
Thank you. Okay, in that case, let's move on to the next section here. So the next section talks about baselines for comparison. So as we described before, there's a uniform set of hyperparameters for all agents that are set up in Dopamine to begin with. And then this allows for consistency over optimization, again, probably to help aid in reproducibility of these different research techniques. And this facilitates hyperparameter exploration as well. In table 1 here, they're summarizing the default versus the published results. And it is shown that there's a minimal action set from the arcade learning environment that's provided by the GIM interface that they used already. So they didn't necessarily have to change those action sets in order to get these results. So here you see the 4 different agents that were described. So DQN, C51, Rainbow, and IQN separately from Dopamine itself. So let's take a moment and just look at this table and see if people can describe what's happening here through each episode termination, the training, evaluation, and so on. Does anyone have any questions in regard to this table itself, or what's happening in this comparison? So this is pretty straightforward to everyone?
Yes.
Yes? Okay, great. I just want to ensure. I know sometimes looking at the tables and the figures is probably going to add the most value for people that are visual learners. So I want to ensure we take a moment for that. Okay, so moving on to the next section then. So here, after we're looking at that table, in figure 3, we look at Space Invaders versus Sequest, where we have the 4 agents compared. And again, we're looking at the published versus the default settings. And of note here, in Sequest, changing the dynamics between algorithms really made a difference in the default versus the published settings. So again, I want to take a moment and just allow people to look at this figure, especially if you did not have an opportunity to read the paper in advance, and ensure that you understand what's happening in these 2 gaming environments. And if anyone doesn't understand, again, please do not be shy in asking questions. So why do people think that in Space Invaders, IQN performed kind of more erratically than all the other agents in their average score?
That's an excellent question. I don't really understand the nuances of the different algorithms enough to really comment on that. But I'd sort of have a question as to why the published settings are more erratic than the default settings. In some cases, it looks like default settings are doing better, but it might just be what I'm able to read off of the.
So one of the big factors for stochasticity is the use of sticky actions that the published settings weren't using. It's a more difficult setting because without sticky actions, essentially when you take action A in step 1 and then you take action B in step 2, that's exactly what's happening. But with sticky actions, when you take action A in step 1 and then you take action B in step 2, action B might not actually be executed. You might just, the environment might still execute action A with some probability. So that's what we mean by sticky. It's kind of analogous to like when you would play these Atari games back in the day when the joysticks would get kind of dirty and would get kind of stuck. So you press the button and the button remains stuck for longer than you wanted it to remain stuck. So sticky actions adds this level of stochasticity to the games which otherwise are deterministic.
So one quick question on this. How did we y'all come up with this default settings? They seem to be outdoing the published settings.
They're not, quite the opposite actually. So you have to look at the y-axis. The scale is very different.
Okay, okay.
If we can make this a little bigger even for people. So yeah, here it looks like the scale on the y-axis goes from 0 to, what is this, 40,000? Or is that millions?
I think it's 1,000.
1,000, okay. And then the x-axis looks like it goes to, what is that, 150 million?
Yeah, that is the same for both. That's just the number of iterations you train for.
I see.
But yeah, the y-axis is very different. That this is the scale of y-axis is very different, and this is because of the sticky actions. So it's a lot harder to play with sticky actions, and that's why the score is so much lower. So the change in dynamics could mean that certain algorithms in Sequest, Space Invaders is quite deterministic. Sequest has a bit more, it's a more difficult game. So what this suggests is that under sticky actions, IQN seems to be more robust than C51 for dealing with these stochastic environments, at least initially.
Thank you. Any other quick questions before we move on? Okay, so from John, do sticky actions help the distributional algorithms perform better in more deterministic settings?
I don't know if it helps them, but I think perhaps they're more robust to sticky actions than other, like something like DQN. But I don't think it helps necessarily, although I can't say that with certainty.
And then there was added, because there is less degeneracy, is that correct?
They add more stochasticity. So like a deterministic all of these environments are represented as Markov decision processes. So when you're transitioning from one state to the next under a particular action, if it's deterministic, you will always end up in the same next state. But when you have stochasticity, you can end up in a number of states. So having stochasticity makes it a more difficult problem. And perhaps the distributional, we don't fully understand yet how it's achieving its highest performance. It's an active area of research of ours. But because it's representing a distribution over value functions rather than just the expected value function, it seems like it's almost like taking auxiliary tasks. So it ends up trying to learn about more about the environment than just something like DQN, where it's just learning the expected value, and so that might make it more robust to stochasticity, because it is able to maybe learn a little bit about the stochastic nature of the environment, which DQN might have a harder time doing.
Great, thank you. Okay, let's move on to the next section. Okay, so in section 4, they talk about revisiting the arcade learning environment through a test case. And here they continue the investigation that was done by Machado, I think is the person's name, et al., which is a standard methodology for evaluating algorithms within the arcade learning environment. And here they plot the DQN agent against C51 or Rainbow, but not both of them simultaneously. And they also look at episode termination, and they want to define those to be similar to when a human would stop playing the game. So here that would be when that human would run out of lives or when the game is finished. And so based on that, they define game over as the termination condition and life loss as when a player would lose a life in the game. And this life loss adds an artificial episode boundary in the replay memory when you're running this framework. And if you want to set this within the gin config option, you would do the Atari preprocessing.terminal on life loss equals true. And they gave this example in the paper itself. Let me go to that section. So again, this is set up in the default settings for DQN. I think I passed it. Yeah, here. So this is how you would set it if you wanted to run this experiment. I'll make this a little bigger for people. And so in this specific figure 4, you're looking at the difference in performance under 2 different conditions. So that includes the life loss as well as the game over. And this was run in Asterix, Breakout, and Space Invaders. And of note, life loss here improves performance in simpler games, but it can hinder the performance in more complex games. In that case, the agent cannot learn consequences of the loss of life, which could be what's adding to that problem. And this, of course, is disabled in the default settings, which was also based on recommendation of Machado et al., the original researcher and group that established that idea for this kind of research. So again, let's take a moment just to look at this figure and see if anyone has any questions based on what's happening here in each of these gaming scenarios when testing the DQN and the Rainbow agent with game over and life loss options enabled. Okay, so we do have a question in the chat. Does life loss handle games where players can buy more lives?
I don't think you can buy more lives in any Atari game. Not that I know of, at least.
Okay, any other questions?
Yeah, so it's possible that in other games, like these settings are really specific to the arcade learning environment, which is for Atari games. So it's possible for other environments, if you can buy lives, that essentially becomes a new action that the agent can take. And in that sense, I don't think, I think the only termination that would make sense in that sense, in that game, is game over. Yeah.
Okay. So unless there are other questions, I think this section is pretty straightforward. And we can move on to performance. Okay, so it was stated within the paper for training data, the game frames were experienced by the agent. For each iteration, there were a fixed number of frames, and that was rounded up to the nearest episode boundary. And then there were two schedules for running each job. One that did training, which just took or measured the average score during training. And then one that was called train and eval, which included evaluation runs where the learning was stopped. And you can see this depicted in figure 5 here, which has the difference in reported scores between training and evaluation. And the authors note that there was little difference found between the two, the regular training and the training and evaluation combined. So they suggest that you could restrict this to just the training curves as enough, or to be sufficient for doing experimentation. Any questions on training and performance evaluations? I actually do have a quick question for Pablo. Did you guys just do the DQN and the C51 agents in this case?
Yeah, we just tried those out, mostly because, so we submitted this to iClear and it was unfortunately rejected. So we were dealing with a paper deadline and we just didn't have enough time to run all of the other agents. Even at Google, you have limited numbers of GPUs.
And do you plan on testing out the other ones in the future?
Maybe. I mean, I think the exercise here was just to see, test whether it's worth even running evaluation runs for these agents. These plots suggest that it's not. The code still supports it, but it slows down each one of your runs. So these plots suggest that you can just plot training curves, and so that way you can train your agents a lot faster. I don't think there's a ton of value in running this with, for instance, Rainbow. I did run some experiments and the results were about the same. But to run 5 independent runs for Rainbow for all of these games, that's essentially 15 GPUs, and that I can use for other research that I'm running right now.
And how much time would that take, out of curiosity?
It takes about 5 days to run an Atari game.
Great.
Which is something that's still not great. We'd like to run these faster.
Definitely, thank you. Any other quick questions or comments before we move on? Okay, so Alex Torax has asked, do you know about Go Explore, a new algorithm from Uber, which reaches 2 million points on Montezuma?
Yeah, so I do know about that. I think it's pretty interesting. I don't think it's an algorithm that can necessarily be applied to other types of games. There was some handcrafted rules specifically for Montezuma that allowed it to reach that score. It's still incredibly impressive that they were able to I mean, they basically solved the game. I think the paper was really interesting. There are some really neat ideas. I like that idea of downsampling the frames so that it gives you more generalization. But again, I think some of the things like the handcrafted rules specific for Montezuma, like whether you have a key and that type of thing, doesn't easily carry over to new games. So I think it's an interesting paper, but I don't think the problem of exploration has been solved yet. It is a step towards that, but there's still a lot of unanswered questions.
And another quick question in the chat, does Google train dopamine agents using Google Cloud Services?
Sort of, I guess, but it's an internal cloud service. But you can train these. You can train an agent on if you do have on Google Cloud. If you have a server with a GPU, you can just pip install Dopamine and train it there. So we have like our own internal cloud, and that's what we use. It's essentially the same thing. It's just for those of us that have been at Google long enough, we're just more familiar with that system. But we could train on the regular public-facing cloud as well.
Okay, so let's move on to the next section. So sticky actions and performance. So we talked about this a little bit before, how sticky actions could potentially affect the performance of each of these agents in different learning environments. So in the original arcade learning environment, this potentially rewards agents that can memorize sequences of actions to achieve high scores. So when you implement sticky actions, this provides a stickiness parameter that increases the probability that the environment will execute the agent's previous action as opposed to the one that was just selected. So as Pablo described, like if you are playing this in real life and your button gets stuck, in that case, that specific action will take place instead of the next one that you select. And this implements a form of action momentum, which I'm not quite sure what was meant by that, an action momentum. Pablo, would you mind describing that?
Yeah, so what it means is that when you take an action, there's a chance that that action will still be used in the next step and maybe in the step after that. So it decays, that the likelihood that that action will remain stuck decays with each passing step. The use of momentum, I mean, the term momentum means that like if you have a particular motion, it's easier for that motion to sort of taper down than to stop immediately. It's also a term that we use in optimization. So some algorithms add momentum, which means that the gradients where they're pushing you, in a particular step, that direction will still be considered for the future steps as well. I unfortunately have to leave now because I have to go pick up my kids.
Not a problem.
But it was great listening to all your questions and discussing with you. Thanks for organizing this, Lara.
Thank you, Pablo.
Yeah, try out Dopamine.
Thanks, Pablo.
Bye.
So we'll continue for the rest of us that are still available. So in order to change the default here in the gin config options, for the sticky actions, you would just select the runner.stickyactions is equal to false. And this, of course, was referenced in figure 4 point here, under 4.3. So runner.stickyactions is equal to false. If you want to change that. So obviously it's a default action within this environment to begin with. And then in figure 6, you can see the difference for the sticky versus the non-sticky actions. And this, as noted, the sticky actions usually reduce performance And they, of course, improve performance in some cases, for example, the rainbow playing Space Invaders. Does anyone have any quick comments or questions in regard to sticky actions and performance in these different arcade games?
It looks like in Pong, all of them are consistent. It's only in the asterisk and the Space Invaders where the sticky action, non-sticky action is doing much better.
Definitely.
Any reason why only in those two, and in Pong all of them are, does it have any effect?
Well, I wouldn't know since I'm not the one that performed the experiment, and unfortunately since Pablo has left, we won't get an exact answer, but oh, here, look, it looks like someone in the chat said maximum number of points in Pong is capped at 20.
Okay.
So that could be a reason.
Okay. That makes sense, yes.
Yeah. Okay, any other questions or comments? Figure 6. Okay, and to wrap this up, they do talk about related work. So again, obviously, reinforcement learning and deep reinforcement learning is a very hot topic right now within the AI ecosystem. So there are a lot of other deep reinforcement frameworks that are being developed, which are referenced within the paper that they suggest that you check out. I've listed them here as well for reference. There's also other individual agents that have been developed. So currently DQN was originally released in Lua. And again, that was done by DeepMind. There are PPO implementations and Impala, which is also open source. All of these individual agents are open sourced if you want to look them up and learn more. And then some regular reinforcement learning frameworks as well that do not include the deep network architecture. So if you're curious about those, they're also referenced here for you to look up and do more research. In general, they wanted to conclude this paper by saying, Dopamine was designed to be a single GPU focused on value-based agents and running in an arcade learning environment. And in the future, they plan to build it out to include more policy-based methods, other types of environments as described earlier, including continuous environments, first-person environments, and so on, and then also distributed methods. So that's their hopes going forward. And I'm sure, I know Pablo didn't say this and he's no longer on the line, but this is open sourced. And of course, since he's mostly working on this himself at this point, I'm sure he would love help. So if if you have available time in your schedule and this is something that you're really interested in, it might benefit you and them to look at the code itself and see if you can add to it. The code is available open sourced on Google's GitHub here under Dopamine. There are instructions to adding to it, installing it in your local system and so on. You can submit a pull request. Of course, understand it'll take them time to review it and approve any pull requests. I've also added some additional resources here in these slides. That includes the original blog put out by Google AI announcing Dopamine. Pablo also did a presentation for our Latinx and AI Coalition research workshop at NeurIPS in this past December. So I've included slides from his presentation there. And then some other resources that I think might be valuable to you if you're interested in this type of work. So many of you, I'm sure, are familiar with Suraj Raval. He's done a few videos and released some code also describing dopamine and the mathematics of dopamine. So if you want to dig a little bit deeper into those areas, feel free to do that. Lex Friedman is a researcher and now also a lecturer out of MIT who's putting out some really great quality videos in different areas of deep learning and AI, as well as a podcast. And so I've referenced his deep reinforcement learning video here. There's another one by a gentleman named Xander under a YouTube channel called Archive Insights, where he does an in-depth introduction to reinforcement learning. That one's about 20 minutes long, so not too bad. And then for fun, if you follow Jabril's on YouTube as well, he describes making his first machine learning game using reinforcement learning techniques, which I think would just be very fun for you guys to check out. And then, of course, this framework and a lot of reinforcement learning is originally based on theory and concepts taken from the dopamine neurotransmitter, which, of course, gives the name of this research framework. At least that's where Pablo got it from. So I included just 2 links. If you're curious about how dopamine, the neurotransmitter, actually works, there are 2 videos linked here, a 2-minute neuroscience video on dopamine, and then what is dopamine as described by a doctor. That's online. And so again, if you want to be involved with our Meetup group more in depth, please, if you didn't get this from Meetup, if you got this from another source, to join us, please join our Meetup. We're at meetup.com/artificial intelligence deep learning enthusiasts. You can also find us on GitHub. We have had other sessions, not just our not just our research, AI research discussion sessions. If you would like to lead a research paper discussion group like this, if there's a specific topic you would like to go over, we do have instructions here for how to propose a session with us as well. Personally, I will be hosting one about once a month on different topics, everything from more technical topics like this in reinforcement learning to things about social impact and the ethics of AI and bias in artificial intelligence. So we really want to cover the spectrum within AI. And we used to host as well sessions on the deep learning book weekly. So, we're not hosting those any longer, but if someone else would like to pick those up again, that would be great. And if not, feel free to go into our GitHub to review the previous sessions. And then, of course, if you want to learn more about our organizations, Accel AI Institute, we're a 501c3 nonprofit, so check out our website. Our subsidiary org, the Latinx and AI Coalition, especially if you identify as Latinx or, are an ally and support Latinx individuals working within artificial intelligence, please check out that website. And if you are able to, since we are, a nonprofit and really driven by donations, if you're able to contribute to our open collective, it's pretty straightforward. We have different membership types for that. So you can, do something as small as $2 a month where you're considered a robot, or you can do a one-time donation as well. And that's, of course, appreciated. So I hope that you can join us going forward in the future through one of our, different methods. And like I said, this will be, this video is recorded. It will be posted on our YouTube channel. So that's, if you go under YouTube, just look up Accel AI. And then these slides will also be distributed through our Meetup group and posted on our GitHub. So thank you everyone for joining us today. We really appreciate your interaction and your questions. And I look forward to our next session. Will be posted, I'll put the details up pretty soon and have a date for you shortly. So thank you guys.
Thanks a lot, Lara. This was very good.